Welcome to the first distance learning lesson that we'll be doing. Um, First off, guys, hopefully you're watching this every day. Either I'm going to be posting a video every day, or I'll be giving you a Khan Academy video to watch. Um, so just make sure you do those, okay? Secondly, we are going to be switching up chapters. I think the best way to do this, seeing as we may be out for a while, uh, is to start working on a separate chapter, mostly because this chapter is a little bit easier than the factoring that we've been doing. So hopefully once we come back into school, that's when we'll start factoring again. So we are going to move on to chapter 10. Now chapter 10 is talking about radical functions, and we'll throw in a little bit of geometry in this as well. But it's mostly talking about radical functions. Now, if you remember, we talked about some radical expressions before when we talked about our square root functions, when we changed from a rational expression to a radical expression. So we do have a little bit of understanding what a radical expression is. But now we're going to talk about what we can do with radical functions. So first off, a radical function is anything that's in the form f of x equals the square root of x. Okay, so this is a radical function. Anything that looks like this is considered a radical function. Now, there's a couple things we have to talk about here. First of all, the expression that is underneath the radical, which in this case is just x, we call this the radicand. All right, radicand. And I apologize for all the clicking. As of right now, I don't have a stylus. I should be getting one eventually. So right now I'm kind of using my mouse, so that's why this is not the best drawing as well. So this is called the radicand. And the radicand is actually very important here because the radicand cannot be a negative number. As we know from talking about the radical expressions that we did a couple of chapters ago, we can't have a negative number underneath the radical. And since we can't have a negative number underneath the radical, we know that the radicand always has to be greater than or equal to 0. And that's going to come up in a second. So the radicand is always greater than or equal to 0. So that's actually very important here. So when we do this, there are a couple things that we're going to do. We're obviously going to look to graph this, but before we go and graph this, we want to talk about two things first, the domain and the range, just like we always do. So my domain is actually going to be pretty simple. The domain is always going to be x such that, and then we're just going to take my radicand and set it greater than or equal to 0 and solve for x. So in this case, it's very simple because it's just x is greater than or equal to 0. But in the case where we had something maybe like this, where we wanted to graph the square root of, let's say, 2x minus 3, if I wanted to find the domain of this, I would take my radicand of 2x minus 3, I would set it greater than or equal to 0, and then I would solve. So I'd have to add 3 to both sides. 3's would cancel. I'd be left with 2x is greater than or equal to 3. Divide both sides by 2, in which case I'd be left with x is greater than or equal to 3 halves. So here, my domain would be x such that x is greater than or equal to 3 halves. So it really all depends upon what the radicand is. So to find the domain, you take your radicand, set it greater than or equal to 0, and solve. That's how you find the domain. Now the range is just as easy. The range is found, and it's always going to start y such that, but the range is found by looking at the end of the function. I could have a plus a number or a minus a number over here. It could be something like I could have the square root of 2x and then at the end, outside of the radical, plus 4. Well, whatever this number that is getting added to the radical is, that is where your excuse me, where your domain, or sorry, your range has to be. So in this case, seeing as we're adding nothing at the end of my radical, this would be y such that y is greater than or equal to 0, because again, nothing means 0. If we go back to the example over here, my the number added to the end of the radical is 4, so my range would be y such that y is greater than or equal to 4. Whatever you have at the end here, that's what y has to be greater than or equal to. Even if it's a negative number, if this was 2x minus 4, this would be y is greater than or equal to negative 4. So that's how we find the domain and the range of our radical expressions. Okay? So that's the first part of this. Now, we're going to figure out what we can do in order to graph this. So when we look to graph a function, okay, so let's say I wanted to graph the function f of x is equal to 2 square root of x. Okay, and then I wanted to state the domain and the range. Well, just like we do with everything else, we want to create a table. So we're always going to create an XY chart. Unlike everything else, though, where we would create my x's to be -2 to 2, seeing as this is a radical expression or a radical function, we know that the radicand can't be less than 0. It can't be a negative number. So the number that I'm going to start my chart with here is going to be the first number of the domain. So that means I need to figure out what my domain is first. So just like we said in the previous one, the domain, you take the radicand, set it greater than or equal to 0, and solve. So in this case, it's going to be x is such that x is greater than or equal to 0. Because again, the radicand is x. If we set it greater than or equal to 0, there's no solving that needs to be done. So that would be my domain. So what that means is I'm going to start my x's at 0. So my first x is going to be 0. Then I'm going to go up from there. Now, I'm also probably not going to want to go up by ones, because if we think about it, yes, we can do the square root of 1, but do we know what the square root of 2 is? Not particularly. It's going to be a decimal. If you want to do that, that's fine, but it's going to be a little bit harder to graph decimals. So what I always do is I try to make this a number that can be the square root. What I mean by that is making what's underneath the radical something like either 0, 1, 2, 4, 8, 16, wait, not 8, sorry. I was just going by positive numbers here. 0, 1, 2, 4, 16, 25, 36, because these are all perfect squares. So it will make it a little bit easier to take a perfect square and take the square root of it. That's simple. If you don't like doing that, that's fine. You can always just go x being 1, 2, 3, and 4. So if I have my x, my first x is 0, my next x is 1. So I'm going to plug the 1 in here. So this is going to be 2 times the square root of 1. Well, we know the square root of 1 is 1, and 2 times 1 is 2. Now, I didn't do this one up here. We should probably do this as well. 2 times the square root of 0. Well, the square root of 0 is 0, and 2 times 0 is 0. So this is what I'm going to show you here. So this is, if I don't go by my method here of putting perfect squares, let's just say my x was 2. If I did that, I'd have 2 times the square root of 2. Now, I don't know the square root of 2 off the top of my head, so here I'm going to have to go to a calculator. So if I go to a calculator and I type in the square root of 2, sorry about this, pulling up my calculator here because I don't even know it off the top of my head. Now I just have to find where the square root function is. Again, very sorry about this. Why can't I find square root function? Okay, well, I can't find it. So go to trusty Google. And the square root of 2 is approximately 1.41. So if I take that and I multiply it by 2, I get approximately, and again, this symbol here means approximately, 2.83. So you can see why it may not be advantageous to just go 0, 1, 2, 3, 4, because you're going to get some decimals there. But it's fine. So let's go with if I went 4, if I plugged in 4 for x, I'd have 2 times the square root of 4. Square root of 4 is 2. 2 times 2 gives us 4. So we're able to get this xy chart that I can use to graph. Now the only other thing I would want to do here is we have the domain, we also need to find the range. But like we were saying in the previous one, range can be found by looking at the end and saying, well, what is being added or subtracted? In this case, nothing. So if nothing is being added or subtracted in the end, it's just going to be y is greater than or equal to 0. So I have my domain, I have my range, now I just need to graph the function. So I go to my chart, I go to graph, I have the point 0, 0. So I could plot the point 0, 0. I have the point 1, 2. So I plot the point 1, 2. I have the point 2, 2.83. So that's approximately 3. Not exactly 3, but close. And then I have the point 4, 4. Okay. So whenever we're graphing a square root function is always going to have what we call a soft curve or a smooth curve shape to it. So we start at the one point that we started with, and we're going to connect my points on it with a smooth curve. So I'm just going to kind of connect all these points and start to curve this out. And that's going to be the graph of f of x equals 2 times the square root of x. Now notice though how I didn't continue going in this direction like we would normally do. A square root function is a little different. A square root function is going to stop at a specific point. It will not continue on in both directions. So that's why we have to use this point first. We have to figure out what my domain is so that I have a starting point. So that's going to be my starting point, and then I only go in the one direction. So this would be the graph of f of x equals 2 times the square root of x. Now let's just do one more so that we can get a little bit of a practice with all different types of our graphs here. So let's say, sorry about that. So let's do another practice problem to make sure we understand what we're doing here. So let's say we had the function f of x equals 3 times the square root of x plus 1, and then on the outside of the square root plus 2. Okay, so first thing we should do is we should find our domain and our range first, because that's going to help us graph it. So if we look for the domain, like we said before, the domain is just taking the radicand, setting it equal to 0, and solving. So if I were to take my radicand of x plus 1, setting it greater than or equal to 0, and solve it, I'm going to subtract the 1 from both sides. So I'm going to have x is greater than or equal to -1. So my domain is going to be x such that x is greater than or equal to -1. Then I do my range. My range is whatever is being added or subtracted to the outside of the radical. In this case, it's 2. So my range is going to be y, such that y is greater than or equal to positive 2. So there's my domain and range. Now I need to create my graph. So I'm going to start off by making my XY chart, and I'm going to start my x values at whatever my domain starts at. So my domain starts at -1, so I'm going to start my x values at -1. So to make this a little easier, let's just go in number order. So we'll go -1, and seeing as it's everything greater than -1, we're going to go -1, 0, 1, 2, and then we'll throw 3 in there as well. So now I'm just going to take each of my x values, and I'm going to plug it into the function. So I'm going to get, for the first one, I'm going to have 3 times the square root of -1 plus 1 plus 2. -1 plus 1, that becomes 0. The square root of 0 is 0. 0 times 3 is 0, plus 2 gives me a positive 2. I'm going to do that for the next one. 3 times the square root of 0 plus 1 plus 2. 0 plus 1 is 1. The square root of 1 is 1. 3 times 1 is 3. Plus 2 is 5. I'm going to do that now for 1. 3 times the square root of 1 plus 1 plus 2. So we have the square 1 plus 1 is 2. The square root of 2 is approximately 1.41. And then the square root of 2 times 3 is going to give us approximately 4.24. And then plus 2 will give us approximately 6.24. Now again, all of this can be done on a calculator. Okay? But you want to do it the exact way that I did it. Simplify everything underneath the radical at first, then take the square root of that number, then multiply it by anything it's being multiplied by, then add whatever is being added at the end. Okay, so again, if we did this with 2, we would have 3 times the square root of 2 plus 1 plus 2. So I'm doing everything underneath the radical first. 2 plus 1 gives me 3. So then I'm going to do the square root of 3 on my calculator, and I'm going to get approximately 1.73. Then I'm going to take that, and I'm going to multiply it by 3, which will get me approximately 5.19, or about 5.2. And then I'm going to add 2 to that, and that's going to get me approximately 7.19, or 7.2. All right, again, these are both approximates. Remember, that symbol means approximately. All right, then I go to 3, to the last one here. 3 times the square root of 3 plus 3 plus 2. Oh, sorry, this should not be a 3. This should be a 1. 3 plus 1 is 4. The square root of 4 is 2. 2 times 3 is 6. Plus 2 is 8. So I now have all of my points. Now I get to go and graph the function. So again, I create my xy plane. Now I know I'm going to have a y value of 8, so I should probably make my y a little bit bigger. So I'm going to create my chart here. Again, if you have graph paper, this is much better. Or if you have a way to print out graph paper, that would be very helpful as well. Because then you're going to see, even with me doing it on here, it's not the best, but it's a good enough interpretation here. So I'm going to start by plotting the point -1, 2. So I go to -1, 2, and I create my point there. Then I have the point 0, 5, and I plot my point there. Then I have the point 1, 6.24, which is a approximately here. Again, when you're plotting decimals, you just want it to be close. Then I have the 0.2, 7.2. So we're about here. Then I have the 0.38. And I can see that a kind of curve is happening here. So I'm going to start at this point here, not go past it this way, but just connect all of these points with a smooth curve. And that would be the graph of f of x equals 3 times the square root of x plus 1 plus 2. So now that we know how to graph a square root function, now we're going to talk about sort of reflections and translations of our functions. So whenever we graph a function, that first function that I showed you, the function of the square root of x, that's called my parent function. So again, we'll put that up here. So if we had the square root f of x equals the square root of x, this is what we call the parent function. So again, the graph of the parent function looks something like this, if we remember correctly. We have our point 0, 0. We have our point 1, 1. We had the point 2, about 1.4. And we had the point 4, 2. So we had something that looked along the lines of this. This was our parent function. Now the parent function is basically just the most basic of all of the functions that we have. So when we go and we look at any sort of reflections or translations, we have to look at what we're doing to the parent function itself. So in order to do that, we want to look at anything that we could possibly do to this parent function. Meaning, if I ever wanted to graph y equals a times the square root of x plus h plus k. Okay, and this is very similar to the one that we had just previously done. All of these, a, h, and k, will do something different to our parent function. Okay, so the first thing is a. A is going to show us two different things. First, A is going to show us if our graph gets stretched or compressed. Now what I mean by stretched or compressed is if I have an A that is greater than 1, a 2, a 3, a 4, my graph is going to stretch itself out, meaning it's going to get a little bit less of a shortening here. It's going to kind of stretch itself out upwards. Okay, that's if A is greater than 1. Now, if, let me get a different color here, if A is between 0 and 1, meaning it's some sort of a fraction like 1/2, 2/3, then it's going to compress itself. It's going to get a little bit less stretched out. Okay, so if it's greater than 1, it gets stretched. If it's between 0 and 1, it gets compressed, like that. So that's the first thing that I look at. The second thing is if A is negative. Now, if A is negative, what's going to happen is that my graph here is actually going to completely flip across the x-axis. All right, but it's still going to hold true with this stuff. So if I have a negative, the negative parent function is just going to be like this. If I were to have like a -2, it's going to stretch itself out this way. That would be the -2, And then if I had, let's say, -1/2, then it's going to compress itself over here. Okay, so like I said, this would be an example of if A was something like -1/2. This is if I have a regular A, meaning A is 1, or in this case, -1. And then this one here, this one would be if it was like A was equal to -2. Okay? Up top here, this one we said this was if a was equal to 2. Here, this is a being equal to 1, or the parent function. And then this one here was if a was equal to a regular positive 1/2. Okay, so as we see that a can take our function and stretch it, compress it, or it can flip it across the x-axis. So those are the two things that a can do for me. Okay, so it can either stretch or compress based on our number, if it's greater than 1 or between 0 and 1, or it can flip it if it's negative. The next thing that we look at is the k. Okay, if we look at k here, k is going to determine how many units up or down I move this entire graph. All right, and that is again dependent upon what the number is. If k was something like -2, then it's going to go down 2 units. If k was +3, it'll move it up 3 units. Okay, so if k is positive, it moves up. If k is negative, it moves down. And then the last thing is h. H is going to determine if I move left or right. Okay, now this is the one that's a little bit weird. So here, oh no, well, yeah, kind of. Because normally you'd think that if it was positive, you would move to the right, and if it was negative, you'd move to the left. It's actually the opposite. So if h is negative, meaning h is less than 0, you're going to move that many units to the right. And then if h is greater than 0, you're going to move that many units to the left. Okay? So 3 things that you want to look at when asked about the transformation based on the parent function. The first thing you look at is a. If a is greater than 1, it gets stretched. If a is less than 1, it gets, or between 0 and 1, it gets compressed. Let me write that for you. If a is greater than 1, we call it a stretch. If a is between 0 and 1, we call it a compress. And then if a is negative, it gets flipped. Sorry if I spelled that wrong. I think I spelled it right, though. Okay? And then the last thing I'll just write for you is k. If k is positive, meaning it's greater than 0, it'll go up. And if k is less than 0, it will go down. Okay, so let's do a practice problem talking about our transformations and our translations and reflections based on our parent graph. So let's say I asked you to graph the function, we'll call it g of x is equal to 2 times, let's go with the square root of x, plus 2. And not only do I want you to graph this, but I want you to compare it to the parent graph and state the domain. Okay? So first thing we should do here is look at all the different parts that we have. First off, this number out front that's being multiplied, this is my a. I don't have a number inside, so I don't have an h, or my h is just 0, so we don't worry about it. But then outside, this is my k. So if we remember back to the other one, my a is going to tell me whether it gets stretched, compressed, or flipped. Because my a is 2, and my a is greater than 1, that means that we are stretching my graph here. So the first thing I'm going to say in terms of connecting this to my parent function is that my graph gets stretched. Now I don't have to say anything like that. I don't have to say anything more than that. If you wanted to say the graph gets stretched by a factor of 2 because my a is 2, that's fine. As long as you say the graph gets stretched, that's all that we need. Because there's no h, I don't have to worry about saying if it moves to the left or to the right. But then I move on to my k, and we say that since my k is 2, and again from the previous example, if k is greater than 0, that means it moves up. We then also say end moves up 2 units. When we move up or down, left or right, we do have to say the amount of units that it moves. So in this case, because my k is 2, we're going to know that it moves up 2 units. So this right here, this would be your explanation as to comparing it to the parent graph. So if I ever ask you to compare it to the parent graph, that's what I'm looking for. The graph gets stretched and moved up 2 units based upon my a, my h, and my k. But now the second part of this was to graph it and to state the domain. So again, we should know how to state the domain at this point. The domain, we just take the radicand, set it greater than or equal to 0, and solve. My radicand is just x, so that means that my domain is going to be x such that x is greater than or equal to 0. If I wanted to graph this, I start my xy chart. Take a different color. I start my xy chart at the number that we have in the domain, so we'll start at 0, and then we can just go up. We'll go to 4 here, and then I take it, I plug it into my function. So I do 0 first, I do 2 times the square root of 0 plus 2. Square root of 0 is 0. 2 times 0 is 0. Plus 2 is 2. Same thing for the next one. 2 times the square root of 1 plus 2. Square root of 1 is 1. 2 times 1 is 2. Plus 2 is 4. 2 times the square root of 3 plus 2. We said the square root of 3 was approximately, what was it, 1.4-ish? No, sorry, oh wait, we're not even on 3, we're on 2. Sorry about that. Square root of 2 plus 2. I'm getting ahead of myself. The square root of 2 is approximately 1.4. That's approximately 1.41 times 2 will give us approximately 2.83, and then plus 2 will give us approximately 4.83. Now we can do 3. 2 times the square root of 3 plus 2. And as we said before, the square root of 3 is approximately 1.73. Then we multiply that by 2, which gives us approximately 3.46. And then we add 2, which gives us approximately 5.46. And again, please remember, these are just approximates. They are not exact. Here, now we can plug in 4. 2 times the square root of 4 plus 2. Square root of 4 is 2. 2 times 2 is 4. Plus 2 gives us 6. And now we have enough points that we can just go and graph our function. So I take my points here. I have the point 0, 2, which is right here. 1, 4. 2, 4.8, which is almost 3, but not exactly 3. 3, 5.6, which is approximately right here. And then 4, 6. And again, as we see, we do see a nice smooth curve happening. I know that point's a little bit off. It should be up a little bit more. It should be up there. But that's fine. We do see our smooth curve happening. And there we see the graph of the 2 times the square root of x plus 2. Now, if we look at that parent function that we had said before, remember the parent function was the one that looked like this. And if we take a look at the differences between what we said here, the graph gets stretched. Well, as we see, it's definitely a little bit more stretched out than our parent function, right? We have a little bit more of a stretch going on in the upward direction. And it moved up 2 units. Well, if I go from here, we moved up 2 units, so everything would get moved up those 2, except once we see the stretch happening, obviously that's going to change it a little bit. But that's what we would see. We would see it get stretched and moved up 2 units. So that's what I mean by a transformation or a translation of our parent function.